All right, welcome to Chemistry 120, The Joy of Chemistry. My name is Brent Eldridge. I'm the professor at Bluegrass Community Technical College in Lexington, Kentucky, and we are going to be using Chemistry in Context as our textbook for this course. And what I want to do is record a video of those topics or concepts within the chapter that I believe you may have difficulty with. I'm always willing to do more of these videos if you'll request them, and then you can request them through my email at brent.eldridge@kctcs.edu. So chapter 1 is about the air we breathe. We generally take the air we breathe for granted in our lives. This chapter talks about composition of air, how the percentage of nitrogen, oxygen, and other gases in air. We talk about pollutants in terms of parts per 100, parts per million, parts per billion. There's also a section on classification of matter, which is really important. I would say that's probably one of the most important concepts in Chapter 1 is looking at matter. When matter is anything that takes up space, how do we classify it? Is it a pure substance or is it a mixture? If it's a pure substance, is it a compound or element? If it's a mixture, is it homogeneous, meaning it's all one phase, like the air that you're breathing? Or is it heterogeneous like sand and water? So there's a section on that. They want you to also familiarize yourself with the periodic table. And then we talk about atoms and molecules, how we represent those. We cannot see an atom or molecule under a microscope, so we have to have symbols or formulas or molecular models in order for us to visualize those substances. Finally, we'll look at balancing chemical equations and bringing up another term called Avogadro's number. The rest of the chapter is about the types of pollutants that are in the air, how they are formed, and what the impact of these pollutants are on our lives. So that part I'll expect you to read. You may want to read that a couple of times. There will be questions on the quiz and exam based off sections 1.13 and 1.14. All right, so let's get started. I think the first thing that we should focus on is just following along with the book. What do parts per million mean? So chapter 1, and we're looking at something like ppm. There's also parts per billion, and there's also parts per 100, although we don't often hear parts per 100. So the parts per 100, the reason why we don't hear that very often is the amount of nitrogen in the air that we breathe is 78%. 78% nitrogen. All right, and the chemical formula for nitrogen is actually N2. It's a diatomic gas, di meaning two, two atoms bonded together, diatomic. So generally, instead of saying parts per 100, we generally say 78%. But what does 78% mean? Well, it means that it's 78 atoms, or let's be more specific, molecules. When we have two or more atoms bonded together, now we're talking about molecules. So molecules are two or more atoms bonded together. So when we say 78%, we're saying that there are 78 molecules of nitrogen per 100 particles of air. And you may be saying, well, why did you say particles? Because particles allows me to talk about molecules, which are two or more atoms bonded together, and it also lets me talk about individual atoms. Now, molecules that naturally occur in air are, again, the nitrogen, the oxygen. Other molecules are carbon dioxide. Actually, that's two different atoms, and there's actually three atoms, so this would be triatomic. Triatomic. And then also water vapor. That's what gives us the humidity in the air. And again, triatomic molecule that consists of two different atoms. And then there are atoms of a noble gas such as argon. Noble gas is out of, if you look on the periodic table in group 18, that's the last column on the right of the periodic table, you'll see this gas in that column, and that column is called the noble gases. So again, parts per hundred, we don't hear it very often, and it means the same thing as number of parts out of the total number of parts per hundred. And so 78% means 78 out of 100. So it's just like your quiz or exam. If you got 5 out of 10 right, you got 50%. You got 5 right out of the total 10. All right. So can we make this parts per million? Well, what is a part per million? Well, a part per million is equal 1 divided by a million. Now, chemists, we don't like to write numbers like this. What if we forget a zero? We're off by a factor of 10. So we use scientific notation. We'll say 1 divided by, and the way we'll represent a million is 1 times 10 to the 6th. So how do we get that? Well, the decimals here in a million, we're going, oops, let's go back. The decimals here, we're moving it, having some technical difficulty. The decimals here, we're moving it 1, 2, 3, 4, 5, 6 to make it 1, and then all of these zeros are acting as placeholders, and that's what the 10 to the 6 represents. So if I take 10 times 10 times 10 times 10 times 10 times 10, that's 10 to the 6. 1, 2, 3, 4, 5, 6. That's 6 terms of 10. And so instead of writing that all out, we just write 10 raised to the 6th power. So this is the way we generally represent large numbers in chemistry. It's much easier to write, and we're not as likely to make a mistake. All right, so if I want to make this parts per million, then I have to have a million particles. So we would say 1 times 10 to the 6 particles. So if we multiply 78 times 100, 78 divided by 100 times 1 times 10 to the 6th, what this is 100 could be written as 1 times 10 to the 2nd. And because this is 10 to the 2nd here, and this is 10 to the 6th up here in the numerator, if you remember from your math classes, 10 to the 6th divided by 10 to the 2nd is the same as saying 10 to the 6 minus 2, which means 10 raised to the 4th power. So you may want to brush up on your math. There's a little math that you need to know. When you divide exponents, you actually subtract them. So that gives us 10 to the 4th. So up here for parts per million, we'd have 78 times 10 to the 4th nitrogen molecules per million particles. 1 times 10 to the 6 particles of air. All right. Now, as a scientist, a lot of times we don't want to leave a number 78 times 10 to the fourth. It gets confusing. So we will move the decimal from here to here. And by doing that, we've made the number 7.8. And that power of 10 that we just lost is included in the exponent. So now this becomes 10 to the fifth. And the easiest way to remember that is think about what 78 times 10 to the fourth is. 78 times 10 to the fourth would be 7, 8, and then 4 zeros after it, like that. So it'd be 780,000. All right. So 7.8 times 10 to the fifth, it's the same thing. We're just moving the decimal. We're moving the decimal one more place. So 78 times 10 to the fifth is 7, and then 8. But see, the decimal was here, and then 1, 2, 3, 4. So we get the same number, 7.8 times 10 to the fifth. The decimal was here. 78, the decimal was here. So 78 times 10 to the fourth is, we'd write it out, 7.8 times 10 to the fifth. Same number, same number. It's just that this way of writing a number is called scientific notation. And you say, well, what's so special about scientific notation? It's only one digit, the decimal, then the rest of your significant digits, the digits that are non-zero and that are meaningful. And we'll talk about that later. All right. So again, how did we find out how much nitrogen in parts per million are in the air that we breathe? We took the percent nitrogen that occurred in air. We broke that down into parts per hundred, which means 78 out of 100 particles of air are nitrogen. And then we want to know what it is in a million particles of air. So if we multiply this, the particles of air canceled out, and we got 78 times 10 to the 6 molecules of air. And we have to divide by the 100, so that gives us 78 times 10 to the fourth, or we could write that more correctly. Let me just write that right here, 7.8 times 10 to the fifth nitrogen molecules per 1 times 10 to the 6 particles of air. All right. We could do the same thing for a part per billion. We're running out of room, so let's move over to the next slide. So right now we have 7.8 times 10 to the fifth molecules of nitrogen per 1 times 10 to the 6 particles of air. And a part per billion is 1 particle out of 1 times 10 to the ninth total. So 1 out of 1 times 10 to the ninth. So if I want to know how many nitrogen molecules are in a billion particles of air, I'd multiply this by 1 times 10 to the ninth particles of air. All right. Now, in order for these to cancel out, they do have to have the same term. So both of these are particles of air. They cancel out. And this is going to determine how many particles or how many molecules of nitrogen are in a billion particles of air. So again, from our math lesson on the previous slide, we have 10 to the ninth. We're going to subtract 10 to the sixth. That's going to give us 10 to the third. So here's the next step. So 1 times 10 to the ninth divided by 1 times 10 to the sixth is 10 to the third. We're going to multiply that number by this number that we have here for nitrogen. And so when you multiply exponents, you add them together. So what we really have is 7.8 times 10 to the fifth times 10 to the third. So that's going to give us 7.8 times 10 to the eighth. 7.8 times 10 to the eighth nitrogen molecules per billion particles of air. And some of you may be saying, well, how do you get that particles of air? It canceled out up here. Well, this is where we determine the amount of nitrogen in a billion particles of air. But when I want to represent it to someone, it is 7.8 times 10 to the 8th nitrogen molecules per 1 times 10 to the 9th billion particles of air. So we could leave it like that, or we could also multiply this by, we could say, part per billion. Actually, another way we could write this is to say 7.8 times 10 to the 8th parts per billion nitrogen. Could do that. All right. So I hope that's helpful. When you see parts per billion, where will you see this? A lot of times when you look at maybe your drinking water, when you get, if you pay your water bill once a year, generally your utilities company, your water utility, will send out an analysis of the drinking water, and it'll talk about parts per billion of different substances in your drinking water. But that's the next chapter. So it's air that we breathe, and then later we'll talk about the water. All right, the next major concept, I think that, again, students have difficulty with this. Again, I'm assuming that you can read the chapter, that you can, you're journaling in your notebook, you're writing down the words in bold and writing those definitions down. So you're keeping a glossary in your notebook. You are doing the problems that are assigned for each day that are in the syllabus under calendar, and then you're taking your own notes as you read. I can't stress that enough, that read a section, tell me what that section's about, write that down in your own words. Now, I don't collect these notebooks, but they are crucial for you to do well on these timed quizzes and exams. You're not going to have enough time to just go back and reread the whole chapter. You're going to have to pull that information together in your notebook. And I just find that if students do a great notebook, they generally have great success in the class, but if students don't keep up with their notebook, they generally start to falter. All right, so the next concept is to look at classifying matter, mixtures, elements, and compounds. So let's start a new slide for that. All right, so we've talked about matter before. Matter is anything that takes up space. Matter is not light. Matter is not electricity. It is not energy. That's a different form that we look at in chemistry, energy. But in this class, for the most part, we're going to focus on matter, things that take up space. All right? So think about what's around you that takes up matter, takes up space. Your clothes, your shoes, your book, your pen or pencil, your calculator. All these things take up space. Even the air that you breathe takes up space. That's how we know we can take a sealed container, we can pump air into it like the air in your tire, and you know that's taking up space in that tire. It's what inflates it. So even the air that you breathe is matter. So once we know we have matter, we have to make a decision. And the decision is it a pure substance? Or is it a mixture? Now, if you have to guess, what do you think occurs the most in nature? Pure substances or mixtures? Mixtures, absolutely. So, pure substances, it can only be one of two things. It's either an element, which is a group of atoms that have the same number of protons in the nucleus, which give them those atoms similar chemical properties, chemical and physical properties, or it's a compound. And a compound has a very specific definition, and that definition is it's two or more different atoms. It's got to be, there's the key. Different atoms bonded together in a fixed whole number ratio. Now you say, what does that mean? Well, it means this. You know that water is H2O. Doesn't matter where you are in the universe, if we call it water, it's H2O. So the way we represent that is we have an oxygen atom, and then we bond a hydrogen, two hydrogen atoms to that oxygen. So here's the oxygen, and here's the two hydrogens. So here's a model. We can't see an individual molecule of water with the naked eye, even with a microscope. So we have to use symbols to represent what water looks like. And so each one of these circles represents an atom of hydrogen, and the circle in the middle represents the atom of oxygen. So this is two different atoms, hydrogen and oxygen, bonded together. That's a chemical, that's a force that holds these atoms together in a simple whole number ratio. You go, what does that mean? Well, if you believe there's an atom, you either have one or you don't. You can't have half of an atom. You either have an atom or you don't. So that's where we get the whole number ratio, that it's always two atoms of hydrogen to one atom of oxygen. You can't have a half of a hydrogen bonded to an oxygen. And again, this is a compound. It's also a molecule. So what's the difference between a compound and molecule? Compound, two or more different atoms. Molecule can be two of the same atom bonded together. That's the big difference between compound and molecule. Elements, if it's an element, it's on the periodic table. That would be hydrogen, which naturally occurs as a diatomic substance. It could be xenon, could be iron, could be copper, could be sodium. These are all elements. And so, if in doubt, think about looking at a periodic table to determine if it's an element. Compounds, two or more different elements bonded together to form a substance. So sodium chloride, table salt, NaCl. It's two different atoms bonded together to form a compound. So pure substance are pretty easy to find. They're pretty easy to identify. Again, they're not the most common substances in the universe. Most things are mixtures. So mixtures, two or more different substances that occur in a variable composition. There's the key, variable composition. Two or more different substances that occur in a variable composition. So what does variable composition mean? Well, it means you can take a glass of water, which is H2O. You can add 1 teaspoon of salt. You could add 5 teaspoons of salt. So that's variable composition. For every cup of water, you could add 1 to infinity number of, well, I guess I shouldn't say infinity, but you could add a lot of salt to water. And every time you add more salt, you're changing the composition. So that's what we mean by variable composition. Mixtures, there are two types. One is homogeneous, and the other is heterogeneous. All right? Homogeneous means one phase. Like the air that you're breathing, you don't see different phases. It's all transparent. It's all, you can't pick out different parts to it. Like air is a good example of homogeneous mixture, unless your air is really dirty. Heterogeneous, it's going to be two or more phases. Two or more phases. So, two or more phases, like oil and water. If I have a glass and the oil is lighter than water, then you're going to have oil here and you're going to have H2O here. If you shake it up, it gets cloudy because you get these little oil droplets suspended in the water. Still two phases. It's the liquid phase of the water, and it's this oily phase of the oil, or different densities. And that's why you see these two different phases. Even though oil's a liquid and water's a liquid, you're saying, well, that's one phase. Well, they're different densities. They're not coalescing to make one phase. You can distinctly see two different phases, so that's heterogeneous. Number one indicator that we use in physics to determine if you have a heterogeneous mixture is, once you know it's a mixture, if you take this oil and water, and let's say the oil droplets are suspended in the water like this, somebody shook it up or something like that. If you shine a light, like a flashlight, at the water, and you can see the beam traveling through the substance, you can actually see the beam traveling through it, that tells you it's heterogeneous. So you try to shine a light on a gallon of milk, there's so many particles suspended in the liquid of the milk that it reflects the light back and you see it as white milk. If you had a really powerful light, though, you would see the beam traversing through or traveling through the milk. So milk is heterogeneous. Even though it says it's homogeneous or homogeneous, or actually what it says is homogenized, it is not a homogeneous mixture. It is a heterogeneous mixture. What the homogenized means is that they have separated the particles that are in the milk so that they don't settle out. So you shouldn't sit there and let milk set in your refrigerator and expect like all of a sudden it comes back and it's all the white solids are down in the fats or whatever, or at the bottom of the gallon, and then it's just liquid, clear liquid at the top. That doesn't happen because the milk's been homogenized. But it is a heterogeneous mixture. Heterogeneous mixtures, concrete, sand and water. You can get into more technical ones like shaving cream, which is little air bubbles suspended in a liquid. That's what makes the foam. Homogeneous, if you put 1 teaspoon of salt in a cup of water and stir it up, the salt completely dissolves. You don't see any setting on the bottom. That's a homogeneous mixture. Could do the same thing with sugar. Maybe I'm trying to think of some other things. Maybe Kool-Aid dissolves. You got the dye in there, but it's completely dissolved. It's all one phase. You shine a light. Now, what it looks like on a homogeneous mixture is this. If you have, let's just say this cube is filled with air. You shine the light, it comes in on one side and pops out the other side, and you don't see it in the middle. Now you say, well, I don't know if I really see that or not. Have I ever seen that in real life? Sure you have. When you shine your lights from the car, it goes from the car out to maybe a tree out here, and the tree's lit up with your car lights, all right? If that's the case, then the air is homogeneous. But on a foggy night, there's these water droplets suspended in the air that are large enough that causes scattering to occur, and so you actually see the beam leave the car all the way out to the tree. So that's why you don't drive with the high beams on when it's foggy, because all you're doing is it's hitting more of these water droplets suspended in the air, and it obscures your vision. So you always drive with the low beams on when we have fog, which is water droplets that have gotten so large that they do scatter the light, and now the fog is over here is a heterogeneous mixture. All right? Really important concept. Make sure you can classify matter. It's important throughout the rest of the semester because we're going to be talking about all these different forms of matter. All right. Just for a little bit of information, the figure 1.7, the different regions of the atmosphere. On page 21. Make sure you know those different regions. I have seen I've seen a quiz question based on that, it's not something you generally think of, but since we're talking about air, we definitely need to know the troposphere is where we are, and then where's the ozone layer, where's the stratosphere, how high do weather balloons go up, where are the tops of thunderstorms, and then where is the mesosphere. So that's on page 21. All right. The next concept that I think students struggle with is really it's about moles. It's about moles. So let's talk about what moles are and how we use them. All right. The underlying principle in chemistry, if we didn't have this law, then there would be no chemistry. And that is the law of conservation of matter and mass. Law of conservation of matter and mass. And what this law says is that in a chemical reaction, matter cannot be created or destroyed. Now your book has a fancy definition. It says that matter and mass are conserved. But the easy way to remember it is matter cannot be created or destroyed in a chemical reaction. And you say, why is that so important? Well, before this law, people did think, and some people today think things actually vanish, that they actually disappear, that they leave this universe and go some other universe, or they fade to nothingness. But under highly controlled experiments, we know since the 1700s that when we see a chemical reaction, the matter is conserved. And the way we know that is we could do an experiment where we have a container that's sealed, and we have one substance and another substance, and we weigh this so we know what the mass of this whole apparatus is. And when we shake this up, maybe these two things react together and they actually disappear. They look like they're disappearing because they turn to colorless gases. So this is why people think things vanish, disappear. But if we reweigh the entire container, the mass remains constant. That's the law of conservation of mass. That even though it looks like it disappeared, when we weigh it, it weighs exactly the same. So you go, why is this so important? Well, when we look at hydrogen reacting with oxygen to form water, what does this mean? Well, it means a hydrogen molecule, which looks something like this, and an oxygen molecule, which we'll find out looks something like this. This is called a Lewis dot structure. It's coming up in another chapter. The hydrogen bond breaks, the oxygen bonds break, and we get a hydrogen, oxygen, hydrogen bond. So we get something like this. This is called a stick model, where this one's a little bit more specific. It's a Lewis structure model, which we'll come up with later. So right now, if we look at this reaction, it looks like an oxygen has disappeared. The two hydrogens over here on the reactant side, they're over here on the product side, but only one of the oxygens is on the product side. So we know that matter cannot disappear, that it has to be present. So what we need to do here is, in order for this to work out, we're going to have another water molecule over on this side. So here it is. So now you got two water molecules. Now you've got your two oxygens, so this is satisfied. But we have four hydrogens on the product side now, and we only have two on the reactant side, so we need another hydrogen over here. Another hydrogen molecule. So we have two hydrogen molecules. we have one oxygen molecule, and that forms two waters. So instead of writing this all out pictorially, we need to write this in a compact form. So what we do is we stay with the equation that we have up here, and we put a coefficient, that's the terminology here, coefficient of 2 in front of the hydrogen. That 2 represents this one and this one. And we also need a 2 in front of the water to represent this one and this one. Notice we don't have a coefficient in front of the water, the oxygen, which means that if it's in the chemical reaction, that's what this is called, a chemical equation. If it's in the chemical equation, it's understood that there's a 1 in front of that oxygen. It's understood. So this equation is now called a balanced chemical equation. Balanced chemical equation. And the reason why we can write a balanced chemical equation is because of the law of conservation of matter and mass. So you're going to get some practice in section 1.9 on how to balance a chemical equation. All right. So, in reality though, we can't see individual hydrogen atoms, and we can't see individual oxygen atoms, and we can't very easily weigh individual hydrogen molecules or individual, I should say molecules here, not atoms. Individual hydrogen molecules, individual oxygen molecules. So we need to work with a quantity that we can actually see, that we can actually manipulate. So to get to that type of quantity, we have to use a term called a mole. All right. So a mole, which is actually not discussed yet in this chapter. I'm just going to put this on the end here because I want to see where we're going with this. To get to a quantity that we can see or measure, we use the term mole. And mole means 6.022 times 10 to the 23rd. Now, instead of saying this number over and over again, this term has a name. It's called Avogadro's number, or Avogadro, either way you want to say, Avogadro's number. So when working with atoms or molecules of this quantity, called Avogadro's number, we're working with moles. So we're going to use this as a conversion factor later on. When we do a little bit more math, we're going to be using this equality as a conversion factor. And you go, well, this is really throwing me. I don't understand this. Well, it's no different than this. If somebody says you have 1 dozen, that means to you that you have 12. So to a chemist, when we say 1 mole, that means to us 6.022 times 10 to the 23rd. All right. One last thing I want you to be able to do here is going back up to this equation. Oh, before we go on to the next concept, let me just say this. So, to work with quantities that we can measure in on a balance in the lab, what we do say is, instead of saying 2 molecules of hydrogen, we say 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water. So these coefficients can be thought of as individual molecules or group quantity of a mole. So we can say, again, this is what we can say. We can say 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. That's one way we can say it. But if we're working in the lab and we're trying to measure and see these objects, these substances, we would say 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water. And you go, well, why is that so important? Well, if we look at something like sugar, C6H12O6. So here's our chemical formula. If I wanted to draw a ball and stick model, I may put something like carbon, 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 carbon. So there's my 6 carbons, and then I may put OH groups off of that. So we get a O and a hydrogen, and an O and a hydrogen, and an O and a hydrogen. And so we've got our 6 oxygens, and then we need some more hydrogens. And I'm not expecting you to draw this at this point. Let's see what we got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oops, do I have too many? 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, I got too many. Let's take this hydrogen off right there for right now. So this is probably not the correct structure for glucose or sugar, but it gives us more information here. So what I want you to be able to do, though, is this. If somebody says you have 5 molecules of sugar, how many atoms of carbon do you have? All right, so how would you do this problem? Well, you would say for every, and this is how we're going to do all the math in this class. That's why I want to stress this concept here. If you have 1 molecule of sugar, you can set that equal to how many atoms of carbon you would have. So how many atoms of carbon, if you have 1 molecule of sugar, how many atoms of carbon are in that 1 molecule of sugar? You should say 6 atoms of carbon. This is called an equality. Equalities are really important in chemistry. We use these to make conversion factors to be able to do mathematical problems. So, this is what we do. Let's say I have 5 molecules. I say we have 5 molecules of sugar. Now I know how many carbon atoms we have. So I'm going to start with what's given in the problem. 5 molecules of sugar, C6H12O6. Oops. Let's fix that. All right. So we want to get rid of the molecules of sugar. Well, let's keep it C6H12O6. And we want to end up with atoms of carbon. All right? So, from our equality up here, it says 1 molecule of sugar is equal to 6 atoms of carbon. We divide both sides of this equality by whatever we need in the denominator in our conversion factor down here. So we need the molecules of sugar in the denominator. So we're going to divide both sides of this equal sign, equality, by 1 molecule of sugar. So if you do it to this side, you've got to do it to the other side to keep this equal sign in force. So we divide both sides by 1 molecule of sugar. This side becomes 1. Well, that's really important. And you go, why is that so important? Well, you know that 7 times 1 is equal to 7. Didn't change the amount we have. We still have 7. So this part over here is equal to 1. So it's not changing the amount we have. All we're doing is changing from molecules of sugar to atoms of carbon. So we take this and we move it down here, and it's going to be 6 atoms of carbon here, 1 molecule of sugar here. So that's where we get this conversion factor. It came from this equality. The molecules of sugar cancel out, so that tells us, hey, we're on the right track. That's what you're looking for. You want to watch those units cancel out. And then it's 5 times 6, and my answer is 30 atoms of carbon. So if I have 5 molecules of sugar, I have a total of 30 atoms of carbon in that sugar. How many atoms of oxygen would you have? How many atoms of hydrogen would you have? Well, we don't really need to reinvent the wheel here, right? If we look at this, the ratio of carbon to oxygen is the same, so there must be 30 atoms of oxygen. And it's a 2-to-1 ratio of hydrogen to carbon, so we have 60 atoms of hydrogen. Now, I think that's what throws a lot of students too. They go, well, we started with only 5, and now we've ended up with 120. So how can you get more out than you put in? Well, it's kind of like a car. You got one car, but if you start breaking it down into its parts, there's thousands of parts in that car. So here we got this molecule of sugar. We got 5 molecules of sugar. We start breaking them down into the individual carbon, hydrogen, and oxygen atoms, and we end up with a lot more atoms, 120. All right? So focus on this problem. This is like what you see towards the end of the chapter. You definitely need to be able to do these. And we are going to be doing this type of math throughout Chemistry 120. Now, I try to keep the math to a minimum in this class. It's not a math class. I am really focused on the air that you breathe, the pollutants, the mixtures of substances that are in our air. But that part you can read. That part's in the book. But the things I've talked about in this mini lecture are the things that I know that students have had problems in the past, and I want to make sure that we get you some help here. Again, if you need other help, there's something I didn't cover that you're struggling with, just send me an email, and I'll be glad to develop a mini lecture for this. That's what I believe online learning is all about. I understand you can't get physically to the classroom for whatever reasons, and so we try to make this classroom happen through the internet. And I do that by recording my voice and recording what's on the whiteboard here, and you can listen to it multiple times to understand the information. All right. We'll see you later.